Continuing from the earlier video about the Neptune antenna, I found a paper online that shows the copolar to crosspolar isolation of a circularly polarized antenna, and it got me thinking the right way about circular polarization. So I'll present what I found in this paper, and at the end of the video I'll show an intuitive way of understanding how the polarization varies in the radiation pattern of a small circularly polarized antenna. It's easy to see how to think about it, but there are some mental gyrations that will have to happen to see exactly the polarization at all different angles and so forth. But I think it's a valuable insight.
So let's start by parking the Neptune antenna for now. Remember, it's a flat plate array design with circularly polarized radiating elements. So that's the connection to circular polarization. So here's the paper I found. It describes what the authors call a semi-dual polarized monopulse feed. Paper was published in 2023 out of South Korea. And the authors describe a feed for a paraboloidal reflector to make a monopulse antenna. And the feed operates at about 16 gigahertz, which is important for missile applications. The authors didn't build the feed or the paraboloidal antenna. What they did was they used a software application called CST Studio Suite to simulate the electromagnetic fields and calculate the feed and reflector radiation patterns. So the feed looks like this. It's an interesting compound design. It comprises 5 separate antennas where each one is an open-ended waveguide, piece of a waveguide. Now the reason the feed is interesting in the context of the Neptune antenna is because the feed center antenna is circularly polarized. And it's very interesting that the authors also published correctly published a diagonal cut of the cross-polar radiation pattern of the reflector antenna, which is important in Neptune for 2 reasons. Firstly, because it provides some insight into the likely polarization purity of a circularly polarized antenna. And secondly, because thinking through this problem provides an intuitive and useful way of understanding the effect of look angle on the polarization of a circularly polarized antenna. It's not quite like a dipole, based on electromagnetic first principles. So back to the feed as a whole. The center element is a square section waveguide that's used to create the monopulse sum pattern. So of the 5 feed antennas in the feed, this is the only one that radiates. The other 4 antennas are for azimuth and elevation difference patterns, and they're used for receive only. That means outwardly the feed looks like a circularly polarized antenna, so that's pretty clever, even though the difference patterns are linearly polarized. I mean, it's clever from a radar point of view, but from a jamming point of view, I would say, oops, even though it's impossible to jam all 3 channels at once, sum, azimuth difference, and elevation difference, the designers have made all 3 channels separately jammable. And we don't need to jam all of them to cause problems, but I'll come back to that in a separate video. Anyway, here is what I think is the most interesting part. The authors used CST to model the radiation pattern of a reflector antenna using this feed, and then they show the sum channel peak, copolar, and crosspolar gains of the reflector radiation pattern. Not the feed pattern, but the reflector pattern. And the crosspolar gain is correctly shown along a diagonal cut, which is where the condon lobes are. So here's the copolar sum pattern, and unfortunately it's over a very broad angle, so we don't get a good look at the reflector main beam. There's another graph, but I'm not showing it here. The peak gain is about 36.5 dBi. And here's a diagonal cut of the reflector's cross-polar sum pattern. It has a peak gain of about 15.5 dBi. So that means that cross-polar isolation is about 21 dB, comparing the 2 peak gains, even though they occur at different angles. That's maybe a few dB poorer isolation than I would expect for a fairly deep reflector fed by a linearly polarized waveguide. I mean, the experimental one that the authors treat is its F over D ratio, focus over diameter ratio is 0.323. And for reference, the MG13, its F over D is about 0.4. So the MG reflector is a bit flatter. I would expect it to have a lower cross-polar isolation. A bigger isolation, lower cross-polar gain. And if we squint really hard at this graph, it looks like the Bohr-site cross-polar sum gain is about minus 5 dBi, so the Bohr-site isolation is about 40 dB. So again, that's maybe what we'd see for a reflector with a waveguide feed, which, let's face it, that's what this is. And I think this set of graphs shows the expected polarization isolation for a small circularly polarized patch antenna, because the paraboloidal reflector essentially collimates the fields at wide angles and compresses them into a central region. That's one way of understanding this. The reflector acts kind of like a magnifying glass on the off-axis polarization period of a circularly polarized patch antenna, or cross dipoles. I mean, just as it does for linearly polarized feed. This is like one way of understanding why the reflector antenna has high gain. It's compressing everything into the forward direction. It's called collimation. So after all this, what's the correct way to represent the radiation pattern of the Neptune antenna and BrahMos antenna and the rest of those who use radiating elements that are small circularly polarized antennas? Well, we need to represent each array element as two crossed infinitesimal dipoles oriented at 90 degrees to each other, with a plus 90 degree phase shift for right-hand circular polarization and minus 90 degrees for left-hand circular. And I can illustrate an easy way to understand what's going on by showing 3D surfaces of the radiation pattern of two crossed dipole antennas. So here they are. The gain pattern of an infinitesimal dipole looks like a donut, and the E field follows a cosine, the amplitude of the E field follows a cosine pattern in, let's say, elevation for vertical polarization and azimuth for horizontal polarization. The donut shape happens because polarization becomes ambiguous at the poles, so the gain goes to zero, has to go to zero. Anyway, no matter how the vertical or horizontal components of a circular polarization are created, then the far field polarization and gain patterns have to follow the dipole shape, and the electric and magnetic field vectors have to always be tangential to the surface of a sphere around the donut, or we can't have RF power flow away from the antenna. That's because power flow, the pointing vector, P-O-Y-N-T-I-N-G, the pointing vector is the vector cross product of the electric and magnetic field vector. So they have to be, the E and H fields have to be tangential to the sphere so the power can flow away from the antenna or toward it. Anyway, moving away from boresight, so let's look at how the circular polarization radiation pattern of polarization changes as look angle changes. Moving away from boresight in the vertical direction causes the circular polarization to gradually develop ellipticity and become horizontal polarization. Moving away from boresight in the horizontal direction causes the circular polarization to gradually develop ellipticity and become vertical polarization. Moving along the diagonals produces circular polarization because the gain of the vertical and horizontal dipoles both have cosine angle dependence. They're just spatially rotated by 90 degrees. And remember that circular polarization can be decomposed into cross dipoles, one horizontal and one vertical. And in the quadrant areas, there are various flavors of elliptical polarization, all blending from circular polarization to linear polarization, horizontal at the top and the bottom of this picture, and vertical left and right. In any case, to make a mathematical representation of an infinitesimal circularly polarized antenna, like the feed element of BrahMos or Neptune or whatever, I would use just two dipoles rotated at 90 degrees relative to each other. So that's the next step to represent Neptune's seeker antenna correctly, represented in ENGAGE, is to code a pair of cross dipoles and use them as the flat plate array radiated elements configured with the position and count, element position and count as shown in the Neptune photos. And then uncover the whole thing with an ogive radome and work out the vector math to extract the cross-polar radiation pattern. Now, it should be interesting.